Well, hello again out there in remote learning land. Today we're going to chat about the power of graphs, graphing different variables. We've been talking about variables affecting density, right, pressure and temperature. Well, we're going to look at them graphically and see how you can interpret them. And certainly makes it easier to understand things. Make sure you're studying your notes every night, folks, and of course submitting your notes at the end of each day so I could see how you're doing. All right. We're going to start out with a little presentation from a former vice president. You might have heard of him. His name is Al Gore. And he's talking about climate change and how temperature has changed over time. And to prove his point, he has a funny sense of humor. To prove his point, he brings up this huge graph, and he's showing you this cyclic relationship. But watch how he presents it to you.
In all of this time, 650,000 years, the CO2 level has never gone above 300 parts per million. Now, as I said, they can also measure temperature. Here's what the temperature has been on our Earth. Now, one thing that kind of jumps out at you is, well, let me put it this way. If my classmate from the 6th grade that talked about Africa and South America were here, he would say, did they ever fit together? Most ridiculous thing I've ever heard. But they did, of course. And the relationship is actually very complicated.
Okay. Sorry, folks, 1 second. Okay, so he was showing you a cyclic relationship there between temperature and carbon dioxide on this monster graph so that the audience can, really get an idea of what he's talking about instead of just looking at numbers, because let's face it, it's a lot easier to see things visually than just staring at a page full of data. Okay, so I'll read that through. How do we define a graph? Good information there. Graphs are a visual way to organize and present data. Right? Instead of just a pile of numbers, well, now we can see what the trends are. Is it increasing, decreasing? Is it repeating? Is there no relationship at all? All right. Line graphs show how a measured quantity changes with respect to time. Usually time is on the bottom. We call that the x-axis. Distance also can be there, or another variable. And the y is always the one on the side, right? So we call that the y-axis. On the bottom here, we call that the x-axis. But more importantly, on the bottom is where you put the independent variable. Okay? On the side, the y-axis is always where you put the dependent variable. Okay, very important to remember that. All right? So there's your independent on the x, your dependent on the y. All right? Graphs always should get a title. Make sure you put the title in there. All right? And I want to put a couple of graphs up and see how you guys interpret them. So we'll start out with this one here. Okay, classic looking graph there, and it looks like it's just going straight up. So the x is increasing and the y is increasing. All right, and that's the statement you would say: as x increases, y increases. Because remember, this is the one that's independent. It's the one that's controlling the y. So as the x does this, the y does that. All right, we call that a direct relationship. All right. The opposite of that, of course, would be a graph that looks like this. So now as the x is still increasing, now the y is going down. It's decreasing. All right, so your as statement would look like this. As x increases, y decreases. All right, it's no longer a direct relationship, right? We call it indirect or inverse relationship. This is kind of like when the temperature goes up. Things usually become less dense, right? When the temp goes up, the density usually goes down because you're spreading those molecules out. All right, those are your first two. The third one is the classic roller coaster, right? We call that cyclic. And in this case, as x is increasing, y seems to be doing a repeating pattern there. All right, it's predictable. And it's helpful for many things in nature. All right, we call that a cyclic relationship or cyclic. For example, right, the seasons, they are cyclic, right? We are leaving summer and going into fall in just a couple days. Then will come winter, but then will come spring and summer again, and you get this cyclic relationship. Same thing with the tides, right? You get them high, then they're low, high, low. It's repeating. Sunrise, right? Sun goes up, goes down every day. Of course, that's due to the Earth's rotation. We'll talk about that later. Phases of the moon are cyclic, right? You go from a new moon to a full moon, and then, of course, back to the new over the course of a month. Yes, that's where that word month came from. So they're pretty cool, cyclic relationships. Non-cyclic events would be like earthquakes, tsunamis, weather, volcanoes. Harder to predict because they aren't so directly repeating. Okay? Then you get this guy here. As X is increasing, Y is kind of staying the same, right? He's not really changing much. And there it is. As X increases, Y stays the same. We call that a static or no relationship at all, right? It doesn't matter what X does, Y is still going to stay the same. All right, so there's no effect. And your last one here looks similar to the other one, only now X is staying the same, and of course Y is increasing. Of course, it's still a static relationship. There really is no connection between those two, obviously, because one is not affecting the other. Okay, those are your basic 5 relationships, certainly the ones we're going to focus on in earth science. And you got to remember these as statements, right? As this, then this. Okay, so to sum it up, how do we express relationships by using graphs? Hopefully you can put the words dependent, independent in there, variables in there, connect it all together, get a nice answer. Okay. Student calculates the densities of 5 different pieces of aluminum. Please underline that, folks. They're all aluminum. They're all the same material. Hint, hint. They have a different volume, so they're different sizes, but they're still made of the same thing. Which graph best represents this relationship? Well, if you remember, if it's the same material, it has the same density, no matter how big it is, then you would have to go with choice 3. No matter how big a chunk of aluminum you have, it's still aluminum. It still has the same density. Okay, we're going to head back to the GC in a second, and I'm going to give you guys a bunch of graphing relationships. Before we do, can you figure this one out? Chances of human survival versus pollution. Let's see, if there's more and more pollution, that means the water gets dirtier, the air gets dirtier. Our chances of survival would probably head right into the toilet. And what kind of relationship is that? If the X is increasing and the Y is decreasing, hopefully you said the inverse or indirect relationship. Okay? All right. So meet me back in the GC. We're going to work on these together. And I'll take your questions over there. See you in a minute.